Welcome to our discussion. Today, we're diving into a fascinating paper that tackles the challenges of fine-tuning large language models, LLMs. The paper reviews and assesses parameter-efficient fine-tuning, PEFT methods. What are the core challenges that make fine-tuning LLMs so difficult?
The primary challenge is the sheer size of these models. LLMs can have billions of parameters, requiring massive computational resources and significant time for fine-tuning on downstream tasks. Traditional fine-tuning, which updates all parameters, becomes prohibitively expensive and time-consuming, especially for researchers and organizations with limited resources.
So PEFT methods offer a solution. Can you explain the basic concept behind them?
PEFT methods aim to achieve comparable performance to full fine-tuning while drastically reducing the number of parameters updated during the fine-tuning process. This is accomplished through various techniques that selectively modify or add a small number of parameters, preserving the knowledge learned during pre-training.
The paper categorizes PEFT methods. What are the main categories and what are their key differences?
The paper categorizes PFT methods into 5 main groups: additive fine-tuning, partial fine-tuning, reparameterized fine-tuning, hybrid fine-tuning, and unified fine-tuning. Additive methods add new trainable parameters. Partial methods update only a subset of pre-trained parameters. Reparameterized methods use low-rank transformations to reduce the number of trainable parameters. Hybrid methods combine different approaches, and unified methods offer a single, integrated framework.
Let's focus on additive fine-tuning. What are some prominent examples of this approach?
Adapter-based methods are a key example. They insert small modules, adapters, into the existing network, allowing for task-specific adaptation without altering the pre-trained weights. Soft prompt-based methods, like prefix tuning and prompt tuning, add trainable vectors to the input embeddings or hidden states. These methods are relatively simple to implement and often show good performance.
And what about partial fine-tuning? How does it differ?
Partial fine-tuning focuses on selecting a subset of the pre-trained parameters to update. Methods like bitfit only update bias terms, while others use pruning techniques based on criteria like thresholds or Fisher information to identify the most important weights to adjust.
The paper also discusses reparameterized fine-tuning. What's the core idea here?
Reparameterized methods use low-rank approximations to represent the changes needed for adaptation. LORA, low-rank adaptation, is a prime example. It uses 2 small matrices to approximate the changes in the weight matrices, significantly reducing the number of trainable parameters.
Hybrid and unified methods seem to be more complex. Can you briefly explain their approaches?
Hybrid methods combine different PEFT techniques, often manually or through automated search, to leverage the strengths of each approach. Unified methods aim to create a single, integrated framework that incorporates various fine-tuning strategies in a consistent manner.
The paper includes experimental results. What were some of the key findings regarding performance and parameter efficiency?
The experiments showed that many PEFT methods achieve performance comparable to or even exceeding full fine-tuning, while using a significantly smaller number of parameters. The specific best-performing method varied depending on the model and task. Some methods, like prompt tuning, were very parameter efficient but sometimes underperformed. Others, like adapters and LORA, offered a good balance between efficiency and performance.
What about memory efficiency? Did PEFT methods show improvements there as well?
Yes, many PEFT methods also reduce GPU memory usage, especially for larger models. However, some methods, surprisingly, increased memory consumption. QL-OQL, a quantized version of LORA, was particularly effective in reducing memory requirements, making it suitable for fine-tuning very large models.
The paper mentions several applications of PEFT methods. Can you highlight a few?
PEFT methods are useful in multitask learning, allowing models to adapt to multiple tasks efficiently. They are also valuable in cross-lingual transfer, enabling knowledge transfer between languages. Furthermore, they have implications for backdoor attacks and defenses in machine learning security.
The paper concludes with some promising future research directions. What are some of the key areas for future work?
One area is developing more lightweight hybrid PEFT methods that combine multiple techniques effectively while minimizing parameter and memory overhead. Further research into LORA-derived methods, particularly focusing on pruning and quantization, is also crucial. Improving the PEFT library to include more methods would also greatly benefit the community.
And what about the theoretical understanding of PEFT methods?
A deeper theoretical understanding of why PFT methods work so well is needed. More research into the expressiveness and limitations of different approaches would be beneficial.
Finally, exploring the application of PFT methods in computer vision and multimodal learning is another exciting avenue. This discussion has been very insightful. Thank you for sharing your expertise.